Everyone. The research content of this paper is the maximum biplex search on bipartite graphs. A bipartite graph is a kind of graph widely used to describe two different types of vertices, in which the vertices of the same type have no connection, and the edge only exists between vertices of different types, such as customer product networks, user page networks, gene expression networks, and collaboration networks. As shown in the figure, a collaboration network is composed of authors and published papers. There are many cohesive subgraphs in bipartite graphs, such as alpha-beta-go, k-bitrust, biclick, and k-biplex. K-biplex impose a strict enough requirement on the connections within a subgraph, yet allows some disconnections. K-biplex has many applications, such as fraudsters detection. For example, on Twitter and Facebook, to promote certain pages, fraudsters use a large number of fake accounts to inflate the like counts for these pages. In online shopping, they improve the ranking of certain items by adding items to fake accounts' shopping list. Biplex also play a role in online group recommendation and gene expression analysis and business relationship analysis and other applications. Now we give a formal definition of K-biplex. Generally speaking, for K-biplex, its definition is that each vertex can lose up to K connections in a biclick. For example, the number of vertex in the U and V sets of the graph shown in Figure B is 3. Let K equals to 1, then it is the one biplex of the graph shown in A, because each vertex connects at least two vertices on the other side. There are always a large number of K-biplex in a graph, which makes it difficult for users to choose the appropriate K-biplex. Thus, we propose the concept of the maximum K-biplex. Among all K-biplexes of G, the one with the largest number of edges is called the maximum K-biplex. Note that the graph shown in Figure C is disconnected to biplex. So to avoid this situation, we also stipulated that the number of vertices on both sides of the K-biplex must be greater than 2K. Now we introduce the baseline solution. We first prove that the problem is NP-hard, and then propose an MBS algorithm. The main idea of this algorithm is similar to the maximum biclick algorithm. That is, we first enumerate the combinations of all vertices and then verify whether it is a K-biplex. Finally, we select the K-biplex with the largest number of edges. Then for enumerating all vertices, we can describe the search space as such an enumeration tree. Then we proposed two pruning strategies to reduce the search space. One is the degree-based pruning, that is, the degree of all vertices in a K-biplex is greater than K. The other is that any two vertices on one side of K-biplex must have at least one common neighbor. Taking this figure as an example, when searching for biplex containing V4, we can first remove V2 because V2 is not the two-hop label of V4. After V2 is deleted, the degree of U2 and U3 decreases, so they can also be removed. Putting the candidate set on one side, we need to verify the legitimacy of the vertices on the other side. For example, in this figure, we get the candidate sets V1, V2, and V3. And the labels are U1 to U4. The degree of the vertex in the UC satisfies the K-biplex condition, but the degree of V2 is less than 3, so we need to enumerate the K-biplex containing V2 in UC. Then we can get the 2K biplex, that is V1 to V3 and U1 to U3 and U2 to U4. The limitation of the MBS algorithm is that it enumerates all the K biplex, which has highly computation complexity and cannot be approximated.
To further improve the efficiency, we propose a code-based MBS algorithm. We first discuss the range of the number of vertices on each side of K-biplex. Then we can filter the vertex in set V by determining the number of vertices in set U, and then filter the vertices in set U by determining the numbers of vertices in V. After fitting the vertices, we can get a subgraph, which is defined as xy code, given an integer pair xy. The degree of vertices in set U is greater than or equal to y minus k, and the degree of vertex in V is greater than or equal to x minus k. It can be seen that for any K-biplex, there exists an xy code containing it. Then the whole problem can be transformed into computing all xy codes in the graph and then computing the K-biplex in each code. In this way, we can reduce the size of the graph. The calculation of the xy code is similar to that of K code, which is a peeling-based approach that iteratively removes the vertices that unsatisfy the degree constraint. For example, the figure shows 3-3 code when k equals to 1. If we calculate all xy codes in the graph and computing the corresponding K-biplex, it is also inefficient. So we propose a pruning method. If an xy code contains a K-biplex, we can get the upper bound and the lower bound of its size. We prove that the upper bound is x times y, and its lower bound is x times y minus s minus k. where S is the small one of X and Y. So the upper and the lower bounds, if we have obtained a biplex with size P, we only need to calculate those XY codes that may contain a larger K-biplex, and the rest don't need to be computed. For example, if we obtain a K-biplex with a size of 7, then the XY codes such as 3-2 code and 2-3 code can be pruned because their upper bounds are less than 7. We first define the XY star pair and the X star Y star pair. Given an XY star is the maximum value that makes XY star code non-empty, and the X star Y star pair is the integer pair with the largest product among all pairs. Taking these figures as an example, we can first calculate all X-Y star pairs in the graph, which corresponds to the square on the ladder in the figure, and the X star Y star pair corresponds to the grid mark square. We can first calculate the K-biplex in X star Y star core. If there is a K-biplex with the size of X star times Y star, then it is the final result. If there exists a K-biplex but the size is less than X star times Y star, then we search for other XY codes whose upper bound is greater than the current size. If there doesn't exist a K-biplex, then we reduce Y star and then repeat the above steps. In this way, we only need to search with a limited number of XY codes. Then we propose a parallel algorithm to speed up the K-biplex computation. The main idea of the parallel algorithm is to allocate a thread to the power set of each vertex for independent calculation. To reduce the computation redundancy, we propose the definition of vertex domination. Taking this graph as an example, all the neighbors of V3 include all the neighbors of V4, so V3 dominates V4. Then, when calculating the K-biplex, we only need to allocate threads to V1 to V3 because the result of V4 has been calculated in the subsets containing V3. In addition, we also propose a heuristic algorithm. The maximum K-biplex is obtained by a grid strategy. It deletes the vertex with the smallest degree iteratively because the deletion order of vertices has an impact on the result. We choose a different order and then return the largest K-biplex. Then we conduct experiments to verify the efficiency of the algorithm. We can see that on DBLP, we can reduce the size of the graph by more than 19% through XY codes. Our code-based method is 2 to 3 orders of magnitude faster than the existing approaches. At the same time, we also verify the scalability of the algorithm on the synthetic datasets. Then we evaluate the heuristic algorithm, which is 2 to 3 orders of magnitude faster than the exact algorithm. At the same time, although there is no theoretical accuracy guarantee, its actual approximation is more than 0.4. The parallel algorithm can achieve a 20 times speed up when there are 32 threads. Finally, we conduct a case study on real dataset corporate leadership. We find that the maximum Biplex can find more complex structures than the maximum Biplex so as to mine some hidden information. That's all. Thanks for your listening.